Hey guys, this is the first half of the video lecture for Monday, March 18th, I think. And we're picking up where we left off on talking about the hemiacetal and acetal formation. Earlier we talked about the formation of an acetal that looks like this, which came, of course, from the hemiacetal, which is halfway getting to the acetal stage, right? That was acetal, where that's sort of the two ethers you're looking at right here are they came from two separate molecules, two of these ethanol molecules. But of course, that can actually happen with two alcohols that come from the same molecule like that, if it has two alcohols in the same molecule. So in that case, the hemiacetal that's going to form, which by the way, it's a really good idea for you to see if you can figure out the mechanism for this on your own. It's the same mechanism as above. Something like that might be on the test, maybe. And the at this point, right, like remember that this can leave as water once it gets protonated, and then gets pushed off by the lone pairs on this oxygen to reconstitute what appears to be an activated carbonyl, another oxonium ion, and that gets nucleophilically attacked by this other alcohol. That's what is expected to happen, and so the product should look like that, and that's a acetal. I should mention to you that some chemists would actually call this a ketal, because technically it was derived from a ketone instead of an aldehyde. So instead of calling it an acetal, some people would call it a ketal, but colloquially, for whatever the reason, like we would also call this an acetal, whether or not it came from ketone or aldehyde. And I don't know why that's the case. That's just the convention. Okay. Now, the second example, by the way, pause the video if you haven't thought about the answers to these problems yet. Like if you haven't thought about it yet, like it's really, there's not much learning value, educational value in just looking at the answers or copying down what I'm writing as an answer. It's really good for you to think about it. What would be the study material for forming this acetal? And that's the question here. And maybe pause the video here and think about it. Hopefully it makes sense to you that this methoxy group would have come from the methanol, which by the way, remember that's tosic acid. Hopefully you can still draw the structure for that. And the hemiacetal that would have formed on its way, the intermediate would have looked like that, okay? And so the study material would have been, let's see, 1, 2, 3, 4, 5 carbon chain. 1, 2, 3, 4, 5 carbon chain, and on that fifth, you would have had an alcohol, which is right here, and then this would have become that. So that's what we are saying, and it's this carbon that was an aldehyde. And it's kind of an important skill for you to be able to identify the carbon that used to be the aldehyde or the carbonyl carbon, because that becomes important when we look at carbohydrates as hemiacetals and acetals. The carbohydrate, what characterizes them as carbohydrates is like what the word sounds like. Every carbon is hydrated. That's kind of what that means. So every carbon has an OH group, at least one OH group. And here's the carbon that was aldehyde before this would have cyclized, and this would have been the alcohol oxygen right here that would have cyclized onto the protonated aldehyde carbonyl. Now we have a specific word for that. We call this the carbon that used to be anomeric. I mean, it used to be carbonyl. We would call that an anomeric center or carbon. That just means what it was carbonyl. Okay. And the reason why that's important for carbohydrate chemistry is that's the stereochemistry that dictates the important biological properties of the resulting carbohydrates. Because remember, the anomeric center, or the carbon that was carbonyl, was sp2 and flat. So that means, the alcohol that cyclizes onto itself could have attacked it from either the top or the bottom face. And so you can have two different stereochemistry there. And also, that's also the carbon at which things can polymerize. So this would be considered a monomer. This is just a monomer form of glucose that's in a six-membered ring, which is called pyranose. Pyranose is anything that's got a six-membered ring that's sugar or carbohydrate. Here's an example of what we would call heterodimer, because there's two carbohydrate rings together, but the two carbohydrates are different. One is a glucose, the other is fructose, and when those are together in this configuration, that is called sucrose. Which is the table sugar, and hopefully you can identify the acetal carbon here and there, or aka anomeric centers. Okay, and the way that these things cyclize, if you the mechanism of it, I want you to be able to figure that out. Just to write the mechanism, just to simplify things a bit so it doesn't look too complicated. I'm just gonna omit OH groups from each of these carbons. So this is like a simplified carbohydrate structure, but I want you to know that each carbon should have an OH group if it was a real carbohydrate, but the mechanism would still be the same. The carbonyl carbon could pick up a proton. So that's what protons do, they protonate. You might wonder, well, why that oxygen and not this other oxygen? Remember the idea of rapid proton transfer. Proton is always hopping off from one heteroatom to another. So at any given moment, that proton might be on this oxygen or on this oxygen. So while that proton is on that carbonyl oxygen, it gets activated, of course, and so so when you have an activated carbonyl, a weak nucleophile like alcohol could cyclize like so, or attack via nucleophilic addition. In this case, it would form 1, 2, 3, 4, 5, 6-membered ring. I want you to notice that this is your new bond we just formed. And once this gets deprotonated, you have cyclized carbohydrate. And of course, this is a simplified carbohydrate. It's not the real structure. real structure like you see up here has a OH group on every carbon, but it's carbohydrate when it's cyclized is a hemiacetal. Okay. Now that explains the origin of these anomeric centers you see. And like we said, the anomeric center, right, technically we should say that this is a mixture of two. Well, I should have drawn it like that, because this could be, OH group could be either up or down depending on which direction the alcohol cyclized. This is an sp2 carbon, so the alcohol could attack from the top or the bottom face, and you could end up with either these stereoisomers. And so that's what's at stake at the anomeric carbon, right? Because it's a chiral center. And so for that reason, that new chiral center could be oxygen up, like in cellulose, or oxygen down, like in starches. And that's the difference between cellulose and starches. They're both polymer of the same molecule, glucose monomer, but the way they're cyclized is different. That's the only difference there. But that's carbohydrate chemistry for you. Maybe we'll say, oops. And part of the reason why we learn about things like stereochemistry is because it determines the biology. Okay. Now, just to talk about this picture here, remember earlier we talked about how water here is a byproduct, right? And so one of the ways you could drive the equilibrium to the product this way will be that you can remove your another product like water. And according to Le Chatelet's principle, if you're removing one of the products, reaction would shift more towards the product side. And so when you are making acetal and stuff like that, where you need to manipulate the equilibrium like that and remove water from the equilibrium, it's a good idea to have a setup called Dean-Stark apparatus. And the way that works is it's really just a simply this part of the glassware setup in between your reaction flask that's being heated and the condenser that condenses organic vapor. A lot of times the solvent that is used is something like benzene or toluene that's not miscible with water. And what happens is they evaporate at around the same boiling point as water, so the toluene or benzene solvent vapor goes up and gets condensed and drips down. Now, so both toluene and water gets condensed and drips down, but the water is heavier than the organic solvent, so it sinks to the bottom. So once this fills up, the organic solvent like toluene can flow back into the flask, but the water stays there at the bottom. And that's one way you can remove water from the equilibrium to drive the reaction to completion, even though all the mechanistic steps are reversible. So that's Dean-Stark apparatus. This could create an issue if the solvent that you need is a heavier solvent, like chlorinated solvent that's heavier than water. In that situation, I might take a credit for this because I haven't seen anybody describe this setup, so I'm just gonna for now call it the Suyama setup. We've published on this like a little over 10 years ago, but you could use a oxalate apparatus to run this through so that the heavier solvent gets filtered through molecular sieves that would mop up or absorb moisture before it gets dropped down into the flask for refluxing. Now, but because it's a reversible reaction, the acetal formation, you can of course do the inverse of it, meaning that once you have an acetal like this, if you treat it with a lot of water, so remember this means water is the solvent, and some acid catalyst, you could get your carbonyl compound back and the two alcohols back. In other words, it's a reversible, right? Remember, when you have a reversible functional group that you can put on and put off, that could be used as a protecting group. And so, in other words, acetal is a great candidate for protecting group. And so we already discussed how you can put on the protecting group or the acetal. So here's your method for deprotection. So to speak, like if you wanted to protect this ketone right here. Right? So how does the mechanism go? It's really the exact opposite of what we discussed for the acetal formation, so we'll go rather quick perhaps. You have strong acid catalyst, so remember, because of the leveling effect, the strongest acid would be just hydronium ion. And once that gets protonated, of course, it becomes a good leaving group. And if it just left, it would create a carbocation, but the would-be carbocation carbon is also connected to another heteroatom with lone pairs. So because of that, the lone pairs could push that leaving group off, so to speak, to create this, excuse me, oxonium ion. So you could say at this step, oxygen sort of pushes off the leaving group to create this oxonium ion, which of course is extremely strong electrophilic. So if you have a bunch of water molecules in the midst, this could attack that, like so. This would be considered a rapid proton transfer phenomenon. Proton, remember, just moves around, right? So at any given moment, that proton could be on this oxygen, and then if it is, it is a good leaving group. So if the oxygen next door pushes it off, and that's sort of the hallmark of the acetal chemistry, because there's two oxygens on the same carbon, pushing off a group like that can happen. So then now you have this plus the by the the way, this is ethylene glycol. Could pick up the proton to give you your neutral ketone back. Now, protecting group, remember, is very useful because it can mask a reactive or sensitive functional groups like carbonyl. So I should probably show you like an example of how that might be useful. So I'm just going to show you that right here. Okay. All right. So let's say you have this compound that has both a ketone and an aldehyde, and from that you want to make this secondary alcohol molecule while keeping the aldehyde intact. Okay, let's say that that particular structure is like some desirable drug or something like that. So how would you do it? Well, you can't just expect to throw in some reducing agent and you can't expect that reducing agent to only go for this ketone to reduce and not the aldehyde. For one thing, that reducing reagent molecule doesn't know that you only want this ketone to be reduced. So how would you accomplish this? Because if the reducing agent is going to react with either of these carbonyl, the first thing it'll react with would be aldehyde, because remember, aldehydes are more reactive than ketones because it's more electrophilic and it's less sterically bulky. So how can we do it? Well, the one strategy might be we could protect this aldehyde and leave the ketone exposed and then reduce the ketone to the alcohol and then deprotect the aldehyde to get that back. So that would be the idea here. So how would that work? Well, so the last step we're saying is going to be the deprotection of the aldehyde. And aldehyde, let's say, will be protected like that with a cyclic acetal. Okay. And then prior to this step, we would have reduced the ketone. Like so. And then we would make that acetal from the study material, where we just have to add in exactly one equivalent of ethylene glycol and some acid catalyst. Dean stock apparatus to remove the water byproduct would be helpful. Now, you might wonder, why would it just react with the aldehyde? Remember, the aldehyde is more reactive than ketone. So if there's only one equivalent of the ethylene glycol, it would preferentially react with the aldehyde, but not with the ketone necessarily. And this acetal is very stable under basic conditions. And sodium borohydride, remember, you might have to refer to chapter 12 to see the exact structure of that and the reactivity, but it's a basic reagent. It's got a negative charge and whatnot, and that's why this type of synthesis would be achievable. Okay, so this is an example of acetal being a protecting group. So I'll see you in the latter half of the